All right. I'm Stefano, and here is Bruce. We work at Xilinx, now AMD, and we'd like to talk to you about Lopper and what it can do for Xen embedded configurations. Next slide. Yeah. So modern SoCs are complex heterogeneous systems with multiple different CPU clusters. As an example, you might have a Cortex-A cluster, where typically something like Linux runs. There is also a Cortex-R cluster with an RTOS like Zephyr running. And there might be multiple microblades, smaller embedded processors where maybe a bare metal or again an RTOS is running. So all of them on a single SoC. And if you look at the Cortex-A that are the biggest of these cluster I mentioned as example, they have multiple execution modes. So you have Linux running, you have Xen running, you have also trusted firmware, you have a secure world with all the software in secure world like Opti as an example. So system device tree is an extension to device tree to describe all there is on an SoC like this, including multiple heterogeneous CPU clusters and multiple domains. What is a domain? A domain is the collection of hardware resources that something like Linux needs to run, or FreeRTOS running on microblades needs to run, or a bare metal application running on Cortex-R needs to run. Each of them are domains, and actually the word is similar to the one we're using Xen. A VM, right, is a domain, we often call it. After all, it's the same thing. So in system device tree, a Xen VM will also count as a system device tree domain. So the two concepts match one another because the same unit, if you wish. Next slide. So like I mentioned, system device tree, extend device tree, first of all, to describe multiple CPU clusters. That was not possible in the normal device tree. Only one CPU cluster is described. So including the CPU cluster your operating system is not running on. So it just, describe them all. It also describe all of the domains. So you can have, again, you can see a Zephyr running here, Linux running there, Xen running somewhere else. And all of these domains are similar, if you wish, they are similar to a DOM0-less VM description. In fact, I've been trying to keep them similar. So they contain, the CPU is running on the memory and the device is directly assigned. Next slide.
All right, looks like it's me then. And at the same time as Stefano has been working through the system device tree specification, if you will, or architecture, I've been working on some tooling, and we've been at this for several years now, I think 3, off and on, some tooling around it, because either creating the system device trees, which are now even have more information than a standard device tree, they can be even more error prone than working with, they can be even more complicated than working with a standard device tree. So from the very beginning, we started to create some tooling to manipulate them. And that tool became named Lopper, and you can find it on devicetree.org on the GitHub there. I can say it started as a tool for just manipulating system device trees, sort of pruning, hence the name Lopper, pruning little bits of the device tree out or manipulating things. But since then, as we work through system device tree and the various use cases, it's become more of a framework for manipulating device trees and transforming the information, writing different outputs, different things like that. So it became sort of a framework that can still meet the original goal of producing standard device trees to support your existing operating system or platform, because initially, at least, nothing else needs to read system device trees. We can transform it into what they expect. And now, in its framework format, it's sort of flexible. It's data driven, meaning everything is. Lopper itself knows very little about device trees. It can manipulate them, but it doesn't know what you want to do with them until you pass in inputs. So those inputs can be DTS, they can be source format, they can be DTBs, and they can be YAML. And any input can also be an output. Therefore, we can transform between any two of those inputs, outputs, and then write custom ones as well. So the manipulation is done through either input operations that are small sort of unit operations called lops, or they can be actually loaded Python assists that can manipulate the device tree and produce different outputs. And we'll be demoing the latter, which are Python assists to work with our sort of our Xen pass-through device tree format. Kind of like Stefano, I sort of described my next slide while rambling on my first, but I should point out that it doesn't just do, so it always does different levels of formatting, tree manipulation and consistency checking, which all comes in handy when we're working on things like the Xen pass-through device trees, because we need to make sure that we have ways that we could check to make sure two domains aren't sharing a device, or that we are properly manipulating the host device tree. And this sort of, that is what you would call the core of Lopper, but actually knowing what Xen is looking for in a pass-through device tree, that is the sort of thing that is implementation specific and ends up in an assist. And I think we'll just, we don't really want to talk only about what Lopper can do. I could just point out here that we are using it in device trees in this example, but you'll see in some of the releases of software, whether it be Yocto or whether it be from AMD Xilinx, that we're doing things like writing out C files, header files, bare metal drivers, things like that. So if you think you need to manipulate device trees in a way, then you should come find us, and there's probably a way that we can help support what you're doing versus sort of ad hoc grepping and setting and that sort of thing. Stefano, I think let's, again, not too much. Let's go to Xen partial device trees. That's too much Lopper for
good.
What we want to tell you here.
So as Bruce explained just now, the Lopper was originally born as a tool to convert a system device tree into a regular device tree, which is useful, but it's not the problem I'm going to talk to you about today. It's a similar problem, though, and it's another problem that we managed to solve with Lopper, as you'll see as you see shortly. The similar problem is the generation of partial device trees. So Xen, the device assignment configuration on ARM is driven by what we have been calling partial device trees. These are snippets of device trees, not full, not complete device trees. An example is the one you see on the right. There is a top-level pass-through node and a bunch of information underneath it. And what is underneath get copied over to the DOMU device tree. So this is done for two things. One reason is to expose a description of the device to the guest. So in this case, to show the guest that there is a timer indeed. But the other reason is for the configuration, because some of Xen device assignment configuration. Because some of these properties have actually meaning for Xen. It's not just going to copy them over. Some of them are going to copy them over basically just blindly. But some other have a special meaning. Xen is going to look at them and use them to configure device assignment for this particular device and for this particular guest. Next slide.
There's the button. There it is. Yeah.
So the one you see on the top are some of the properties that are meaningful, right? Actually, all the properties that are meaningful. So Xen reg is a special property to configure memory mapping. So mapping the MMIO region of the device into the guest address space. Xen path is a path in the host device tree pointing to the corresponding device. That would be in the Xen device tree pointing to that device. It is used by Xen to fetch and configure the IOMMU for this device. Xen force assign without a UMMU is to tell Xen to continue is okay, even if no UMMU seems to be present. Interrupt parents, funnily enough, I mean, IRQ is meaningful, first of all. IRQ, I mean, the interrupts property is used to remap the interrupts into the guest, but and also to describe the interrupts for the guest. Interrupt parents, funnily enough, is different because interrupt parents normally points to the interrupt controller, but the interrupt controller in the host is different from the interrupt controller in the guest. So the magic value you see there is the one that is used to point to the interrupt controller in the guest. IOMMU property should not be present because there is no IOMMU in the guest, so far at least. And Xen Passthrough is the property used in the host device tree instead, not the guest, the host, to hide the device from DOM0. So as you can imagine, the steps to produce something like this is not really trivial. You need to take the host device tree, copy and paste it into a new, I mean, the host device tree node of the timer in this example. You take it, you copy paste it into a new DTS, new device tree, and then you start adding Xen reg, you add Xen path, you add Xen force assign without a UMMU if needed, you change interrupt parents, and then you start removing things that are not necessary. You remove the UMMU properties and maybe a few others. So, as you can imagine, most people that try to do this get it wrong. Like I had experience with customers trying to do this on Xilinx boards, and rarely it works the first time. But this is not the worst of it. I mean, if you look at this problem, you think about what can be automated and what could be done automatically. I mean, this could be scripted. This could be scripted even in Bash and sed if you wanted. I mean, all of this information is not particularly difficult to fetch from the host device tree and add to the guest device tree. I mean, yeah, I mean, it would be a bit fiddly, but, you know, it could be written. The next problem, next slide, is the one that, you know, not this one, the next one again, that
this
we
one,
already
yeah.
gone over, this one, exactly. This problem is more a realistic example. Obviously, the timer was by nature a simple example. And in this problem, we see something else. Yeah, we have the Xen reg, we have the Xen path that we need to automatically generate, we have interrupt parents that we need to fix. Again, maybe 3 lines of sed, not great, but could be done. But things get really difficult when we start talking about clocks. So most devices have they're connected to clocks and they have a clock hierarchy. As you can see from the bottom right in this slide, the clocks property is pointing to 2 clocks in there. And for each clock, then there is a clock controller. There is a whole complex hierarchy of clocks. Now, the trouble is, the Linux, not always the clock need to be changed, actually, for the device to function properly. On Xilinx boards, I would say, is often the case, you don't even need to touch the clock. It will work. Problem is, the Linux drivers at boot time, more often than not, wants to be able to probe the clock, read the clock, and often change the clock. Maybe change the clock to exactly the same frequency it was before. But it's still a read and a write operation. The point is the Linux driver doesn't find any clocks, it will fail the probe and refuse to continue. What you have is a non-functioning device in your guest. So now we are in the business of importing clock hierarchies from the host device tree into the guest. And this, I can tell you, is more art than science. It takes several attempts from experts, and it's basically black magic. So this is where we came to Bruce and asked for help.
All right. So yeah, as Stefano was saying, figuring out the way to do it because of Lopper as a framework, there was multiple different ways we could do it. And there's a current prototype solution that we're working on that is actually already up in the GitHub repository. But the big thing was that we wanted to sort of, the things that Stefano described, manipulating properties, copying groups of nodes, following p handles, those are all sort of core Lopper functionality. There's just things it can do. So in an assist, to take and stitch those things together to either drop clocks, chase clocks, change interrupt parent, those sort of things are trivial, but we did need to write an assist to do it. So obviously what Lopper would bring is, the ability to read a device tree, convert it to its internal format. We can look at the devices, do the manipulations of both the new pass-through tree as well as reaching back into the host device tree to add those Xen pass-through properties as an example. And then it can either use the output capabilities to write the DTS, or we can directly write the DTBs. I do a little bit of both in the demo to show we can. And then even wrote another assist to trigger the final bits of the process to generate the bootable U-boot information, sort of the image, if you will. And one of the things that sort of I insisted on when looking at it was that we didn't want to hard code all throughout this pipeline, no hard coded Xen knowledge, in the sense of there was certain things like power domains. There was certain nodes that we did want to include and other nodes that we didn't want to include. So I wanted to make it so those were at least command line options when we're running Lopper. Makes the command line more complicated, but it means that we have the flexibility to include properties, and that sort of thing on the fly. Also, I split the functionality in sort of a general extract assist, because that's actually useful in multiple situations where we can point it at a node and then pull that node and all the p handles that reference it and that sort of thing and generate a new device tree. And then there's one that runs later that does the final Xen conversion for what it's looking for when it boots. So yeah, and also the goal is to work for, we're demoing a timer as well as, I apologize if there's background noise. There's a large truck driving behind my house right now. Our demo is timer and Ethernet, but you can do it for any kind of device. So it doesn't know what the specifics of any device that we're pointing at. So yeah, so here it is. This is what we'll be showing in the quick demo, and this is sort of how it works. We take this input device tree, which, if you remember the description of Lopper, is a system device tree, but in this case, Lopper doesn't really care. It's just a standard host device tree that we're passing in. It's running a first pipeline called extract. It generates a partial and extracted device tree starting from whatever target node we point at. It then creates the sub device tree, if you will, which gets passed to the next plugin, which is called Extract Xen, and it does things like convert the interrupt parent to the virtual one, converts the generic properties to Xen pass-through, and does those sort of things. And then finally, we write the device tree out and invoke image builder to take all those bits, the two pass-through device trees, the host device tree, read its configuration file, and produce the bootable artifacts that we need. But recently, we've actually improved that, and you'll see in my demo that I'm running one where the initial design is we can take one device, pass it through. I then feed the inputs of that first run back through, and I pass through a second device. That way it's consistent. But it is multiple runs of a Lopper. But we've recently created Image Builder can actually now, if it needs to, you can call Lopper from Image Builder, and it hides the fact that you're running multiple Lopper runs, and then it merges the DTBs into something bootable. It's also something we could do with Lopper, but the point is that what I was saying is that there's quite a few command line options, but we don't expect those to be visible to anybody who runs this. We don't want to trade the difficulties of manipulating device trees by hand for the difficulties of figuring out how to run the tool to generate your device trees. Yeah, I won't go over this. These are just dumps of the help text that I did. So you can see they all work as sort of independent plugins. They all take different information. So there's, the T is the target node that I was talking about. Include the node if you find it. Exclude nodes, and then where you want to write it. And then there's different options for the three assists. So now we wanted to run a quick demo of trying to pass this through. So assuming this works, I will attempt to stop sharing. and I will reshare my my terminal. This is where I'm sure it's going to go off the rails. Do we see a terminal, or has it got me? I think it got me.
Not yet.
Not yet. All right, let me try window share. Oh, actually clicking on share helps. Now can you see a purplish
Yes. Yeah.
terminal? Yes. Okay, all right. Well, one hurdle, and they started the truck up behind my window. So again, I apologize if there's white noise in the background. So this is what we're going to run here. This is a it's some prepared, and I should mention, put in my Yocto plug. A lot of this is available in meta virtualization, and the whole demo, the build of sort of the microblaze and the A72 or whatever the cores there we're running, the application cores. I'm going to make it available to be buildable and run from meta virtualization, but I haven't had quite time to update and finish that yet. So we're using a little bit of a captured version. So anyway, the point is I started the first QEMU. We're starting the second. I just want to show that DOM0 has boots, that DOM0 has Ethernet, and there's no timer. So in the demo, what we're going to do is we have two domains. One is running Zephyr, and one is running Linux as a DOMU, and we'll attempt to pass the timer to Zephyr and pass through the Ethernet to the Linux domain, and they should, the point is they will come up. So when we show up here, you can see Ethernet ETH0 is been captured by and pass through. And if we switch over to, we just have a loop back and we have nothing. So now the goal is to do what we've been talking about for 20 minutes, is to create those pass-through from the host device tree, create pass-through device trees for the timer, pass that to the Zephyr domain, create a pass-through device tree for the Ethernet, and pass that to the DOM running Linux, and have DOM0 not touch them, and have them be available and come up for QEMU. So I will restart the microblaze just to get us ready. And so, yeah, the first, as I mentioned, it's 2 runs of Lopper. We're not going to fuss too much about the command line options, but I may point out a couple things on the way through here. So we're running, it didn't work out so well. No, we won't do that. It's running Lopper. You can see it takes an input file, which is the mpsoc device DTS. It's writing out a second device tree called mpsoc boot DTS, and then the pipelined assists are separated by dashes on the command line. So it is asking it to extract the timer node. It's asking it to include the XencMP firmware, the interrupt controller, exclude the interrupt controller, I could say, some pin control, some domains, and some different things. And then it is running the extract Xen assist. And finally, it's writing it out into a timer compiled DTB, an actual DTB that we will be feeding into the configuration, the image builder run to create the bootable U-boot information. So it ran, it said, it dropped the mask property power domains, it wrote out the timer, and it found the reg, and it did the extension that it needed to do and copied it to XenReg. So if we take a quick look at the extracted tree DTS, this is what was created. This is the generic part of it, but you can see, yes, it created the extracted node, it created the buses, it brought in the timer firmware, and it brought in some clocks that might be required to run it. And it also at the same time, if we diff the mpsoc DTS with the one in progress, when it rewrote the device through, it also reached back into the host device tree, and it added Xen pass-through to that node, so DOM0 won't touch it. So we could boot right now, and we would see that the timer is available to Zephyr, but in the goal of not boring everybody, we will just run the second stage of the pipeline, which is basically this. It's the same run of Lopper. Well, it's the same pipeline, except in this case, it's reading that written mpsock boot DTS as the input. It's looking to find the Ethernet device, same include excludes basically for that. And it's adding one more assist into the pipeline, which is the call of image builder to create the bootable artifacts. So in this case, you can see it did the drops, it did some manipulations, and rather than writing a DTS, which we would then need to compile with DTC, Lopper was writing directly into mpsock DTB in the boot directory. So it's using the ability to write DTBs to directly write the DTS. Otherwise, I could do the same diff, and you would see there was now 2 devices in the host device tree with Xen Passthrough, but that would be the only difference. So if we now, that's it. No, the goal is no human intervention required. You can do this dynamically. You can do this in the fly. You can do it in a pipeline. We can do it on target. There's different ways that we can use this now that we have the ability to yank out the device tree and put it in a format that can be passed to a domain automatically. You can already see that one part is working. There's a timer. Zephyr is printing out as it reads the timer, so we can know that it now sees the. I need a faster machine so this boot wouldn't. All right, so if we look now, Ethernet 0 is now no longer part of DOM 0. If we switch to Zephyr, well, then it's been printing along all the way. So it's now printing out the timer deltas that it's seeing. Now the timer's passed through, and if we switch to eventually to DOM 2, magically it has been passed through the Ethernet, which has been detected and configured and is available. So yeah, that is the entirety of the demo, and it looks like we are closing in on our time, so I will reshare the presentation and we can close up here.
Do you have any questions or any observation that we will be interested in?
We should go to questions now because my Acrobat doesn't even seem to be available for sharing now. So.
Yes, I do have one question, but can you explain all the command line options you passed? Because the part where you pass a timer is quite clear, but then there are some other options. Why do you pass those? How can someone find that you should pass the -X something for whatever reason?
I would say, yeah. So we're not even going over this. So that's a little bit. That is, of course, something that when we run it from Image Builder, you don't ever have to pass. So those sort of options are. You do have to understand a little bit about the hardware and the platform and what sort of general things you do and don't want to pass through. So
it's a bit of an heuristic. So basically the reason is the following. So there are a number of hierarchies beyond clocks, right? There is the power hierarchy, the reset hierarchy, and so on. So at least on our board, power and reset are basically optional. So if you take them out, the driver and the device are fully functional. While clocks, if you take them out, the driver will fail to boot. So the reason for those -S is to say remove power domains as a property, remove reset as a property. If you don't pass them, Lopper will try to pull in all the power domain hierarchy and all the reset hierarchy, which is a lot. It's a lot and is also not needed. So that's the reason for the 2 -S options.
Is Lopper having a way to dump somehow all the dependencies of a device so that someone could find out from those results what he wants to exclude? Because doing on a recursive system where you want to assign something and you need to remove. Having the list of dependencies, that should help the user to find out, okay, those ones I want to exclude, so then you add the minus X depending on the list you got previously. So
well, yeah, I guess if you run it once without minus X, you see the full list, right? Right.
Or you run it. You could run it even without the Xen. You could just run that generic extract one, and it would write out a tree, and that would be starting at that node. It has chased everything in the whole device tree that it found where P handles. Right? Yeah. So you could absolutely do that.
Okay. So you can recursively go in circle and find out what is generated and exclude, and then start over and restart. Okay.
Yeah.
Thanks.
Yeah, there is a bit of still, until you know the hardware, there still is a bit of that trial and error, but we're trying to remove the, hey, I cut and pasted it wrong, or, where I just didn't know this was a dependency. Get rid of those ones and make it about understanding the hardware versus understanding how to manipulate the device.
Yeah, exactly. I don't know enough of another vendor board, but for ours, I mean, basically keeping clocks and removing power domains is generally works. That's generally, so it's not really a per device trial and error anymore, at least.
And I think we're at time.
Right, and any last question before we close?
No.
Right.
Nothing.
Thank you.
Thanks.
Thank you.